By now, I'm sure you've figured out that I love talking about algorithms, and obviously I love talking about trees and applications of trees, but there's something else I love talking about that I haven't gotten a chance to talk about too much in these lectures, and that is data compression. And today, I'm going to get the chance to talk about algorithms and trees and data compression. And that's because the last couple of lectures have been sort of big topics like decision trees and that long lecture on heaps. And the next big topic is binary search trees. And that's going to carry us through 3 pretty long lectures. And so now is another great opportunity to take a bit of a breather, to just do an application lecture, to go dive into some application, for example, applying trees to data compression, and not worry so much about proving theorems, but instead just seeing how the techniques we've been learning can apply in really interesting ways in some subfield. And so we're going to talk about a technique involved in the world of data compression, a classic technique, one of the most important techniques of data compression in my opinion, called Huffman coding. But before I get there, of course, I guess we have to talk about what data compression is and why we want to do it. It turns out data compression is a pretty easy problem to motivate because you are using data compression right now. How do I know this? Because if it weren't for data compression schemes, you would not be able to watch this video. You would not be able to receive this many pixels per second, so probably 30 frames per second of 1080p video along with audio of my voice. It would not be possible to receive that with your internet connection. I don't care how much you pay per month. Your internet connection wouldn't be good enough to receive that much data if we didn't have some way of reducing it to a smaller size. And that's why we have data compression. But the example I'm going to do of data compression is a more general example. We're not going to talk about video compression, because that's a bit of a thing, or audio compression, because that's also a bit of a thing. But we're going to talk about a technique that likely is being used in the compression schemes that are being used right now as you watch this video or listen to this audio. So let's start with text. Here is a passage out of A Tale of Two Cities by Charles Dickens, and it's a passage of English text. And it contains 416 characters. But it actually turns out, if I go looking, there's quite a bit of repetition in this sequence. We're going to focus in this lecture on the repetition of individual characters. That is the fact that there are some characters that never appear and some characters that appear quite often. But there's more repetition than that in this sequence of text. So in fact, there are only 28 distinct characters. They just appear over and over again. So just looking, let's see. We can see lots of instances of the letter T. And in general English text, we probably should expect to see lots of instances of the letter T. I think it might be maybe the second or third most common letter you might see in English, right after E. And similarly, we're going to see lots of spaces. We might see punctuation and other things, but it actually turns out we are only using 28 distinct characters. There are some letters of the English alphabet that do not appear in this excerpt at all. And there are some other letters that are doing quite a bit of work and appearing over and over again. Now suppose that I were to save this piece of text into a text file. Well, typically we store our text files using 1 byte per character with probably, well, what is traditionally called an ASCII encoding. That's a term that's sort of lost all meaning because it's so old, but we still use that encoding scheme. And we store it with 1 byte per character. And in this lecture, because we care about the size of things, right down to a pretty low level, we're going to have to talk not just about bytes, but bits. So of course, 1 byte is 8 bits. And that means in my 416 byte sequence, if I store each character with 1 byte, I'm actually storing about 3,300 bits. Now, keep in mind that a byte is 8 bits, which means that there are 2 to the 8, or 256 possible values I could store with 1 byte. And yet, in my excerpt, I only need to store 28 possible things. And that might be an opportunity to find a way of storing this excerpt of text in less than 416 bytes. Now, right off the bat, you're going to notice I do a lot of sort of toy examples. And when we talk about compression schemes in general, and I'm mindful that I haven't yet defined what that means, when we talk about compression schemes in general, we have to be a little bit careful not to get too specific about things. But for the sake of illustrating the concept, it's useful to work with these small examples with only a few hundred characters and to try and develop a specific scheme for those just to get an idea of what compression can do for us. So because the text only contains 28 distinct characters, I don't need 1 byte per character, because 1 byte gives me 256 possibilities, and I only need 28 possibilities. And suppose now that it's important to me that I find a way of representing this text in as little space as possible. Well, then, of course, I want to jump at the opportunity to store each character in less than 1 byte. So suppose that I store each character using only 5 bits instead of 8. Now, there's quite a bit of other things I have to resolve before it's possible for me to do that, but bear with me for a second. Suppose that I do that. Well, then, what I'm doing is I'm storing each character in 5 bits instead of 8, and so the number of bits I would need is just 416 times 5, which is 2080, and that would be about 260 bytes. Which is a pretty healthy savings. I went from 416 bytes, I went down by about 150 bytes. That's pretty good. So almost a savings of just over a third. And notice how, because I'm using 5 bits, the reason I chose 5 bits is that I guess I have to use a whole number of bits, or if I don't, then that's going to be complicated, so we won't worry about that for today. It turns out it is possible. But if I use 5 bits, there are 32 possibilities for a 5-bit sequence, and that is sufficient to represent 28 distinct characters if I encode each one in 5 bits. Now, it's still up to me to come up with some mapping of character values to bit sequences, and we'll come back to that issue later. For the sake of this example, all I care about is that there is a pretty simple way of reducing the number of bits I use per character. And it's also very easy if I come up with some encoding scheme. So I write a program that takes each character and figures out its 5-bit value. I come up with a mapping of characters to bit sequences, 5 bits apiece. I could then encode this text into a 5-bit encoding. And then I could write a second program, a decoding algorithm, that just took each 5-bit sequence, each one in a row, and just converted it back to its original character. In other words, I could take my text, I could convert it to only take up 260 bytes using a computer program, and then later I could convert it back to its original representation. I could completely recover my original piece of text. And that could be beneficial for a variety of reasons. One of which, I do have enough I think hard disks are big enough these days that I'm not worried about 416 bytes, but you can see the utility of this. If I'm storing data for the long term, maybe I don't want to waste space storing it. I want to store it in a compact representation, even if it means I have to use a program to decode it later. Or maybe I'm sending data over a network connection, and that network connection might be slow. Well, if that's slow, then I want to reduce the amount of time it takes to transmit. And the easiest way of doing that, I suppose, is just to transmit less data. So what we've described here is an example of a compression scheme. And the goal of a compression scheme is to reduce the amount of space needed to store your data. Another way of thinking, a sort of philosophical way of thinking about compression schemes, is that compression schemes are sort of a source of mechanical advantage. They're a way of trading one resource for another. So with a compression scheme, what you're doing is spending a bit of processing time in exchange for saving a bit of disk space or saving a bit of bandwidth. It's a way of trading between resources. And generally it's the case that if you use a more complicated compression scheme that eats up more CPU time, you're more likely to get a smaller result. So if your goal is to save space at all costs, you might be willing to sacrifice lots of processing time to achieve that savings. Whereas in practice, it tends to be that there's a bit of a trade-off. We don't want to use up days and days of processing time just to save a few bytes, but we do want to take advantage of any obvious opportunities for savings because, disks are a finite resource, as is bandwidth, and we want to optimize our use of that resource. Whereas on most machines, including probably your computer right now, and mine as I record this, CPUs are often idle. That is, most of the processing power of my computer is not currently being used, even though I should add, the act of recording this video does in fact involve some data compression, because as I record this video, it is live being compressed into a file that is being stored on my disk. Now in this lecture, because we're just taking a taste, there are entire courses out there about data compression. And I should know, you can go look up my lectures on data compression. But we're only going to consider as a taste of what data compression means, something called lossless compression schemes. And the basic idea behind lossless compression is you have some data, we'll call your set of data D, and you're going to feed it through a compression algorithm that produces another piece of data called C, the compressed data. And if all goes well, although you can't guarantee it always will, if all goes well, your compressed data will be smaller than your original data. And that's great. I can store it on my disk, I can send it to you across a network, and later somebody, you or me, can use a decompression program that converts it back to the original data identically. So the data we start with will be bit for bit, byte for byte, identical to what we end up with. We are not allowed to remove anything from the data. We're allowed to change how we represent it, but this must be a completely reversible transformation. So in a lossless scheme, and one of the reasons we like lossless schemes, because it allows us to avoid thinking about certain variables that are too complicated for our purposes, in a lossless scheme, no differences are permitted between the decompressed data, the result of applying my decompression algorithm, and the original input data. The alternative to that is something called lossy compression. And to be honest, most of the compression you interact with on a day-to-day basis is lossy compression. And in a lossy compression scheme, not only are you allowed to change the representation to save space, you are allowed within a controlled setting, within certain parameters, to actually delete certain parts of the data. Because, of course, if you want to reduce what you're storing, you could always just delete part of it. If you delete it carefully, you might be able to get rid of lots of data before you completely destroy the salient information of the data. And so one classic example of that would be JPEG compression. So what I've done here is actually both of these images at one point have been subjected to a lossy compression scheme. But a lossy compression scheme provides us a parameter that is useful but isn't something we want to think about too much today. So it's true that the techniques we use today, lossless techniques, are pretty much always used as part of a lossy compression pipeline, in addition to other techniques that are designed to help remove parts of the data selectively, removing only the unimportant parts of the data, or the parts that people are less likely to notice are gone. And this can be applied to things like images, because it turns out you can delete quite a bit of detail from an image if you're careful where you do it, before anybody who looks at it will notice that anything's wrong. On the other hand, you can sometimes go overboard, like what's happened on the right. The same thing is true of audio. The audio you're hearing now of my voice has been compressed, and that's been compressed with lossy compression. A lot of information has been deleted, but we know enough about the way that the human ear works to understand that there are certain parts of an audio stream that you're never going to notice because, for example, in the background right now, all sorts of other noises going on. So, my computer's making noise, and there's noise in the building around me, but you're probably not hearing it because you're listening to my voice. So if the audio compression scheme deteriorates the quality of the background noise, you probably don't even notice. And that's a good avenue for saving some space. So the key thing with lossy compression that we don't want to get into today is that there's this extra variable. And the variable can be like a single number, or it could be a whole bunch of parameters, but it's a way of measuring quality, or how much data you lose in a sense. So if you set the quality to a lower number or a lower parameter, then you'll save more space, but you'll end up with less of your original data intact, versus if you use a higher quality setting, you'll end up with more of your data intact but save less space. So it's an extra parameter that's hard to account for, not just because it's hard to deal with lots of variables, but also because quality can be a very subjective thing. What it means to remove data to achieve a quality setting, it goes beyond what we want to think about in a formal mathematical sense. It requires some subjective understanding of the way, for example, human perception works. So both of the two images on these slides actually have been compressed with lossy compression. And I know that for a bunch of reasons, one of which is if you're watching this video, everything in the video has been subjected to lossy compression. So what you actually see at the other end of this has been subjected to lossy compression, whether I compressed it beforehand or not. However, the image on the right has been compressed with JPEG with an incredibly low quality setting, which means we save tons and tons of space, but we end up with an image that looks, to use a technical term, like garbage. On the other hand, that said, although this image very clearly looks like garbage, and it's interesting how culturally, as digital images have become a lot more common, it is pretty much true that most people can sort of tell when a quality problem with an image seems to be some kind of digitization issue. That is, although not everybody knows how JPEG compression works, a lot of people can identify, a lot of non-experts can still say, oh yeah, this is a bad JPEG. Like there is some understanding of the way images look on the internet or whatever as a result of what turns out to be overcompression, or overly removing a huge amount of quality from an image. On the other hand, if you know that you have to, transport this whole image and you only have 10 kilobytes to do it, well, then I guess that's the sacrifice that you have to make. One observation I'll make is, even though this image looks like garbage, consider the fact that you can still tell that it's supposed to be a pear. You can't necessarily tell what's going on in the background, but it is sort of vaguely clear that it's a pear and there are some leaves around it. That's a pretty huge deal. So even though JPEG didn't have very much space to work with, it was somehow able to prioritize what aspects of the image are salient to us, what aspects of the image are important for us to understand what the image is all about. A lot of compression has been applied to the image on the left as well, but a lot more subtly because the higher quality setting has been used. And so there actually are aspects of the image that are missing. Things like the detailed, the blurry background of this, so it is blurry even in the original photograph, but there are certain artifacts in that blurry area that are introduced by JPEG compression. But I'll bet you wouldn't have noticed them if I hadn't pointed them out. And even if I do point them out, they're rather hard to see. And that's because the compression scheme has done its job. However, the mechanics of lossy compression require a lot more than we need to talk about today. So we're going to stick to lossless techniques. That said, remember, a lossless scheme will typically be used as one of the components of a lossy scheme. Typically, a lossy scheme will delete certain bits of the input data selectively and then take whatever's left over and run it through a lossless scheme to try and maximize compression advantage. Now, I should take the opportunity to self-promote here. If you're interested in the mechanics of how lossy compression works or how lossless compression works at a higher level, I do have all these lectures already out there floating around about various details, low-level details of both lossy and lossless compression. So go take a look. Or, look up compression somewhere else as well. Anyway, I want to go back and talk about lossless schemes. And it's good to have a point of reference for this. So there are lossless image compression schemes. So in fact, PNG images are losslessly compressed. If you compress an image with PNG and then decompress it, so return it back to an uncompressed format, you will have something that is identical to what you started with, unlike JPEG, which does selectively remove certain detail to save space. But I think the best reference point for general purpose compression would be the various tools that we use for things like zip files. So you're probably familiar with the idea of taking files and putting them into a zip archive, so that would be the .zip format. And when you do that, not only is it convenient as a way of bundling a bunch of different files together, it's also a nice way of saving some space because the zip format uses a compression scheme to losslessly compress its contents, which is perfect for if you want to email something to somebody and you want to save on bandwidth or you have an attachment size limit. And it's also nice for the internet in general to save bandwidth and nice for the email server to save some disk space. And so we can talk about these general purpose compression schemes that can compress whatever data you give them. And it's up to the scheme to figure out how best to compress the data that it's given. And some schemes are better than that than others. Overall, there tends to be a correlation between a faster scheme tends to give you less compression, but of course it's faster, whereas a slower scheme or one that consumes tons of memory tends to give you better compression. Overall, that's not always the case, but it's often the case. So some popular general purpose compression algorithms include bzip, which is the command line program bzip2, a scheme called deflate, which I think is by far and away the most famous scheme of all the ones I've listed, even though you may have never heard the term before in your life. I'll come back to that in a minute. A scheme called LZMA, which, I don't know, the American part of me I'm going to pronounce that as LZMA, I'm afraid, which is the scheme used inside of the 7-zip utility and for various command line utilities on Unix systems like XZ. There's also a scheme called ZStandard, or ZSTD, which is a faster scheme that is meant to, I guess in some sense, it's meant to occupy some of the same market segment as deflate. So it's a fast scheme. It isn't always intended to get the absolutely best possible compression, but it's meant to be incredibly fast, so suitable for typical compression uses, but with high speed, as opposed to things like the LZMA algorithm, which tends to be, if you max out the settings, tends to be very slow, consume tons of memory, but in many cases yield amazing compression results. And bzip is generally considered to be a strong compressor, but it is a bit slower than deflate, although it does typically give us better results than deflate. Although interestingly, on the example I'm about to show, deflate actually performs the best, even though it turns out that deflate of the schemes I've listed is the oldest and in general tends to be very fast, but also does not tend to give the best compression performance. Okay, so what about deflate? So deflate is the compression scheme used in the .gz format, which is what you get if you use the gzip command line tool. So you may have interacted with archive files of form .tar.gz, although those aren't as common these days as they used to be. But one format you definitely have seen before is the zip file format. And you've seen it certainly because probably in all the classes you've taken, zip files have been used as a way of conveying information. Everything inside of a zip file, each of the individual components of a zip file, is typically compressed using the deflate scheme. And the deflate scheme was actually originally invented as part of a zip archive compressor. So if you ever need a justification for needing to know about compression schemes, it's look at zip files. Zip files are a ubiquitous thing, and they use data compression. So this table is showing the size of the compressed data resulting from applying each of these standard algorithms to that 416-byte excerpt from before. And what you'll notice, of course, for compression, we want a smaller number. Smaller is better. What you'll notice is that deflate and Z standard, both of which I claimed a minute ago are not going to be the higher performance schemes, actually have the best numbers. And the reason for that is fairly straightforward, which is that typical compression applications these days, so things you're likely to compress these days, tend to be large. They tend not to be a few hundred bytes, they tend to be maybe hundreds of megabytes. And these more recent schemes designed for really high performance compression are optimized more for compressing large data sets. And that means they might have some overhead that results in the overall size being a few hundred bytes larger than their competitors, or adding a few hundred bytes of overhead in exchange for being able to ratchet up compression performance. But you only really get that ratcheting effect once you're looking at inputs that are pretty big. And so the overhead actually works against the other schemes in cases like this, where the input itself is very small. It's relatively unusual to want to bother compressing only 400 bytes using a scheme like bzip or LZMA. It's actually surprisingly common to compress only a few hundred bytes with deflate, because deflate by now, so deflate originated in the early 1990s, it has been bundled into just about everything. There are plenty of ways, there are plenty of times that, for example, your web browser would use deflate as part of sending data back and forth to a web server. Some of those requests could only be a few hundred bytes, and yet deflate is so ubiquitous, it's used everywhere, that it often is used for small things, and it's pretty good for that, because back when it was invented, files were a lot smaller than they are today. I should add, so of course, for reference, that simple trick where I just converted my encoding to be 5 bits instead of 8 brought me down to 260 bytes. Although there's a little bit of, there's something I've done there that's a little bit shady, which is that I suppose I have to tell you how I do the encoding. Like, if I'm changing from 8 bits to 5, how did I map each letter to a 5-bit sequence? Shouldn't I include the number of bytes it takes me to explain that to you as part of the size? So that isn't included in this. So this scheme does look a little bit better than it really deserves to. But notice how, in any event, the other schemes, if I actually run this data through these compression tools, I get something even smaller still, which is evidence that there's more compression opportunities in this data than I saw before. So suppose that I compress the entire book, A Tale of Two Cities. So not just that one small excerpt, but literally the whole text of the book. There's a lot of reasons it's better to think about this as a reference example, one of which is, how do we know how I chose that excerpt, right? Maybe the excerpt has a few too many patterns in it. If I choose the entire book, and the book is something that we all have heard of before, I mean, so I actually have not read A Tale of Two Cities, other than that 416-byte excerpt, but we all know that book exists, and therefore we can sort of agree that I couldn't have gone, I mean, I guess I could have chosen a book that works very well, but it's not like I chose something obscure that just happens to demonstrate good compression. This is a standard, a work that's well understood as sort of a classic work of English literature from its time and its place. And so if I compress the entire contents of the book, and you can get a plain text version of that book in various places, so for example, Project Gutenberg has plain text versions. That is to say, an actual text file that you can run through compressors yourself. So this is an experiment that's eminently repeatable. Then you can run it through these various compressors and look at the resulting size. One thing I will observe is it's no longer possible, if I compress the entire book, to get a 5-bit encoding, because my 5-bit encoding was based on this idea that I was going to only have 28 possible characters. And of course, if I look at the entire book, there are more than 28 distinct characters. There are 73 of them. So if I just reduce the number of bits I use, the best I can do is 7 bits, because 2 to the 7 is equal to 128. I can't do 6 bits, because 2 to the 6 equals 64. If I run it through my general purpose schemes, we can actually begin to see the higher performance schemes finally shining. So if I run it through deflate, deflate is now the worst performing of my general purpose algorithms. It's coming in at about 280 kilobytes. So I'm going to ballpark these numbers during this lecture because I know a kilobyte is not exactly 1,000 bytes, but it'll be fine for our estimates. And you have the whole number here in case you care. Whereas LZMA comes in at 230. That's a healthy improvement. Bzip does an incredibly good job. So bzip is pretty definitively ahead of any of the others at 203. Z standard is doing pretty good too. It's only a little bit behind LZMA, and likely LZMA took longer and required more memory. So Z standard is doing pretty well, and Z standard is the most recent of these schemes. Whereas again, deflate's at 280, but they're all still clustered in the 200s somewhere. That's pretty good, and they're both achieving what we would call a compression ratio of greater than 2, which is we are getting this file down to less than half of its original size. That's a pretty good big deal. Anyway, so I could use a basic 7-bit encoding if I can come up with one, but you can see the savings there isn't very good. I get it down to 650. The other more intelligent compression schemes are doing way better than me at this point. So what I want to do in this lecture is talk about some techniques or think about the problem of generating a general purpose compression scheme. So I want to get some compression performance, decent compression performance on arbitrary binary data. So even in cases where all 256 possible 8-bit sequences appear, and I can't just use fewer bits. So in this book, because the book is written in English and only certain characters appear in the English language, and there are some characters like the percent sign or maybe certainly the @ sign that I probably wouldn't expect to see in a Charles Dickens novel, I can avoid having to worry about those. But in general, any 8-bit sequence could appear in an arbitrary binary file. I want to find some way of achieving compression even on those cases. And if you try it, if you choose a file, if you choose your favorite file type and try compressing it with one of these, all of which you could get on your machine very easily. They're all available for free, and many of them you already have. Open up a command line and type in gzip. And I'll bet that it doesn't say command not found. I'll bet it tells you that program exists because you likely have it on whatever machine you're using to watch this. Whether it's a laptop or a phone, frankly. Whether even on a dishwasher, it's very likely that on embedded systems with an operating system, there is some gzip implementation floating around. Because often gzip is used for low-level things like compress. Well, these days it wouldn't be used to compress the Linux kernel because I think they might be using LZMA or maybe Z standard for that by now. So let's talk about general purpose compression techniques. I'm going to start with a technique that we're actually not going to follow through on, but it is a natural technique, something that we should consider. So for now, let's take a look at this excerpt here, which is an excerpt that's 46 characters long. It's obviously synthetic. I don't think Charles Dickens wrote this. There are only 7 distinct characters. So of course, one option I have, if there are only 7 distinct characters, I could just use 3 bits per character. If I know in advance these are the set of characters I'm going to be working with, I could come up with some way of mapping each of the characters to a 3-bit sequence. And of course, if I use 3 bits, there are 8 possible sequences because 2 to the 3 equals 8. So I could make up a sort of encoding table here. And that just maps each character in my input to a 3-bit sequence. And I could perform the encoding. And if I do that, we can see, okay, so A maps to 0, 0, 0. And hopefully it's clear that an algorithm that would perform this translation is pretty simple. We just figure out where each thing is in the table, and then we output those 3 bits. And then we take all the bits we get, and we batch them together into bytes, because we typically store things on disk as bytes. And how we do that is not really relevant for today. We batch them into bytes and store it onto disk. And so we go from having 46 characters, which would be 46 bytes in an uncompressed representation, to having 18 bytes, or actually 138 bits, which if we pack it into bytes ends up being 18 bytes. That is a pretty good savings. That's a savings of more than 2. So I mean, we're going from 46 characters to something that considerably less than half of that amount. But I can also observe that there are lots of patterns in my input that go beyond a single character. So for example, notice how there are these long runs of A's, and then a long run of B's, and then some C's, and then some D's, and okay, only one E and one F, but then a bunch of G's. And so I could observe, instead of trying to change how many bits I use for one character, what I could do is try and batch together a bunch of similar characters into a single run. So I could store a bunch of pairs instead of just individual characters, and the pairs would be a count followed by followed by the character to repeat. So this run of 13 A's I could store as the integer 13. Let's store it, let's say, in 8 bits, followed by the character A. The run of 14 B's would become the number 14 followed by a B. The 10 C's would be 10 and then C, and then the 3 D's would be 3 and then D. And observe that for many of these long runs, this provides us a pretty significant savings. So whereas previously in my uncompressed representation, these A's would be the character A, so this 8-bit sequence, 13 times, now I only emit 2 bytes, which would just be the number of A's followed by the character to repeat. So that's a pretty big savings. I go from 13 down to 2. Same thing with the B's. Instead of 14 B characters, I just have the number 14 followed by 1 B character. So that's going to be a savings as well. Although there are cases where I don't see a savings, overall I do, and I notice that I go from 46 bytes down to 14, and that's without actually using only 3 bits per character. A good question to think about is, in this sequence, where am I not going to see a savings of bytes? And I notice the E and the F seem to be problematic, because in the original sequence, the E would have been represented by 1 byte. Whereas representing it using a run length encoding, that's what this technique is called, requires me to have a sequence of pairs of the count followed by the character. And that means instead of using 1 byte for my E, I have to first emit the number 1 and then the E. So the E actually goes from being 1 bytes to 2. My compression actually has the opposite effect. Although again, on balance, over the entire sequence, I do see a savings. And of course, I could combine the two representations together. I could use 3 bits per character and also use run length encoding to batch up adjacent characters that are the same into a long run. And that allows me an even better savings. So just to skim back over the different options here, I can go from 46 down to 18. That's pretty respectable. I can go from 46 down to 14. Okay, that's a pretty big deal. So that's a savings of more than 3 times. So this is 1/3 or less than 1/3 of the size of my original data. And if I combine both techniques, I get a savings of more than 4 times. So of course 10 is less than a quarter of 46. That's pretty good. I've gone from 46 down to only 10 bytes. Although there is still something up my sleeve here, which is that if you want to decompress this, don't I have to explain to you how to decompress it? I have to tell you, I'm using run length encoding. Here is my encoding table. So I might actually have to share with you my encoding table. If I share it in advance and you already have it, then you only need me to give you 10 bytes to get my input sequence. Although maybe we should associate some cost with me sharing the table with you. For the sake of this lecture, we're not going to worry too much about how to do that. I will just observe that if we're working with compressed data on the order of hundreds or thousands or millions of bytes, the amount of extra bytes of sending you a table with 100 things or 200 things in it isn't really going to change things too much. I mean, it will be a bit of a disadvantage, but it'll be a very small amount of overhead compared to the overall size of a big piece of data. But for a small piece of data, that could be a significant contribution. So one question, and I've already spoiled the answer to this because I'm too excited by the topic, is will run length encoding always improve compression? It did here. So in this case, both of the examples I used with run length encoding were better than the alternative. Whether I use 3 bits per character or not, I was able to save some space by also using run length encoding. But the answer here is no. It will not in general improve compression, because what if I get a sequence where there are no runs longer than length 1? Well then, if I'm using run length encoding, when you decode the data, you expect that the data consists of pairs, run length followed by character, run length followed by character. And so I have to waste your time with a bunch of run lengths that are just the number 1. And that actually expands the size of my data. Even if I go to a 3-bit representation, so I use fewer than 8 bits per character, I had 15 bytes for my original sequence, and now I have 21 once I've inflated the size with all of these useless runs of length 1. So, of course, compression is a bit of a trade-off and you have to make compromises. In general, not that we're going to care about it today, it actually turns out that formally you can't really expect to achieve compression on every single input. Just like how with algorithms there can be weird cases where one input makes everything explode if you're not careful, with compression schemes you don't want to tailor your scheme to the worst case, because in general there is no compression scheme that will be able to compress absolutely everything you throw at it. Instead, when you design compression schemes, you tend to want to design it so that on a typical input, the kind of input people actually give you, it saves space. Versus on inputs that nobody would ever care about, like random data, it might not save space. It might actually make the data larger. And that's a trade-off, but not one that we care about for today's application. In some applications, though, you can assume that run length encoding will give you a pretty big advantage. So for certain types of image compression, for example, like if I were to image compression that isn't photographic images in particular. For example, if I were to take a screenshot of this slide, and this slide is an image, obviously, but not really a photograph, notice how if I look at the pixels of the slide, many of them are in long runs of the same color. So, there's this green, there's that white, there's this green up here, the blue in the header. And that means if I'm compressing pixels, runs of pixels, I might have lots and lots of pixels next to each other that are identical. And run length encoding could do wonderful things with that. And so there are some domains where run length encoding and more advanced variants of it can result in incredible compression. And one of them is certain types of image encoding, including the type of image encoding you would do while doing PNG compression. So anyway, for arbitrary data, we've already seen we can't generally assume that run length encoding will always give us a benefit, although we could selectively decide whether or not to apply it in the event that it does. Like we could write a compression scheme that examines its data, decides whether run length encoding is useful or not, and then uses it if it is. We're not going to worry about that, just giving it as an example as some other compression scheme beyond the one that we're actually going to study today that's a tree-based algorithm. So we're going to focus on ways to encode each individual character separately using a smaller number of bits than we started with, and ideally choosing which bits to use for which character in some intelligent way. Now, although we're going to mostly focus on encoding single characters using some table of mappings to bit sequences, there's nothing stopping us from actually grouping characters, let's say groups of 2 or groups of 3, and encoding each group into a single bit sequence. So I could make a table that says, okay, AB maps to 000, and then AC maps to 001. There's nothing wrong with doing that, although that is not really any different than the single character case, except that it's a bit more convoluted, I guess. So we're going to stick to encoding single characters via some table that we can use to encode and decode into a representation that hopefully saves us some space. So one thing I can observe about this, one source of maybe some inefficiency here is I encode every single character into 3 bits, but there are some characters that occur more often than others. So some characters are very common and some characters are very rare. And if we think about it, okay, so in real life, by the laws of supply and demand, something that's very easy to obtain, something that's very common or plentiful is, I don't know, to use a colloquial term, let's say it's cheap, versus something that's very rare tends to be expensive. You might be willing to pay more for something that's rare because since there's only one of them, or there are a small number of them, obviously the price will be higher because, there's more people that want it for the number of them that exist. Versus, since B is such a common letter, you'd expect it to be cheap if they were selling them. Because there's so many of them, there should be enough to go around by the laws of supply and demand. And so often I actually use that when I think about this myself. I think F is a more rare character, so it's more expensive. It's a higher value character. And if I think about using a certain number of bits, how many bits I want to spend on each character, if I'm only buying one F, I wouldn't mind having to spend a bit more for the F as long as the price of each A is low, because I have to buy a lot of A's, and therefore I'd like to pay less in terms of bits. So what I'm observing here is that although each character is encoded in 3 bits, so that is, the cost of encoding an A is 3 bits. It doesn't feel as if characters are being fairly valued. Some characters are more valuable than others, and some are less valuable. And a character that appears more often shouldn't be as expensive as one that appears rarely, for lots of practical reasons. Because if I have to encode lots of B's, it's in my interest to use fewer bits for a B, because over time those extra bits are going to pile up. On the other hand, if I only have to encode one F, I suppose I wouldn't mind if F requires, let's say, 5 or 6 bits, if in exchange I might use only 2 bits for A. Okay, so there's a couple of justifications for why I might want to consider a representation where some characters get represented in 2 bits, that is to say the cheaper characters, the ones that are less valuable to me, and some characters get represented in 3 bits. This is a bit of a dangerous game, though. If I'm not careful with this, I could run into trouble. So conceptually, at least, it seems like this might help. So if I go from a 3-bit per character model to a model where some characters are in 2 bits and some characters are in 3, and I choose wisely, so notice how the 2-bit sequences are going to the characters that are more common. Well then, if I encode it, I get 13 bytes instead of 18 bytes like I had before. I am realizing that savings. Because A's are cheaper, then I'm saving money overall when I'm spending my bits encoding everything. Now the problem with this is I have to be careful because if I'm mixing sizes of encoding, I could end up forgetting which character I'm decoding. If every character is exactly 3 bits, it's very easy for me to know which character is which. That is, the first 3 bits are the first character, the second 3 bits are the second character, and so on. Like I just divide the input up into chunks of size 3, and then I decode each one separately. If characters can be encoded into a differing number of bits, then I run the risk of not knowing what I'm decoding at a given moment. This example doesn't illustrate that very well, but I can come up with an example, a pretty nasty one, where I can actually not figure out what I'm looking at when I come to decode it. So consider, let's see, this situation here. Since the order of characters is irrelevant, the example here, like if I take the characters and I just rearrange them, well, I'm using the same encoding, and each character is encoded independently, which means that the size of my encoding is actually independent of the exact ordering of characters, just on how many of each character occur. So that's one observation. But let's take a look at this. So the first 8 bits of this particular sequence are this sequence of bits here. And remember that if you're decoding this, you don't get this helpful legend. You only get the bits. You don't get the spaces either. You don't get to see where the gaps between characters are. I just give you these 8 bits, and I ask you, could you decode this back into characters? And you'd say, sure, I'll just go ahead and use the table. Okay, so let's see, 1, 0. Okay, that's a B. So I got a B, 1, 0, that's another B, good. And then I've got 0, 1, that's a C. And then I've got 0, 0, and that happens to be G. Okay, great, problem solved. But then you come back in a minute and say, no, it wasn't that, sorry. It was supposed to be 1, 0, 1, that's an F. 0, 0, 1, a 0, 0, 1 is a D, and then 0, 0, that's a G. Uh-oh, okay, this is a problem. So the same 8 bits of data could be decompressed in 2 different ways. And if you're decompressing, which one's correct? You have no way of knowing. This is a problem, because if you choose wrong, then there's no way you're going to recover the original data identically. And that means you don't have lossless compression. It's only lossless compression if you are guaranteed, when you are done, after you decompress the data, to have data identical to what you started with before compression. This is a disaster, to be clear. A disaster from a compression point of view, because we're not recovering our data. We might have lost our data forever here. So it's impossible to differentiate in general if I just go around randomly assigning 2-bit sequences to some letters and 3-bit sequences to others. But that doesn't mean that my underlying idea was bad. It just means that it requires a little bit more finesse to implement it correctly. So the ultimate problem is actually just that there are some encodings whose bit sequence is a prefix of other encodings. And so if we go back to the example with BBCG versus FDG, well, the problem there was, if I look at the encoding for B, it is actually the 2 bits for B are the first 2 bits of the encoding for F. So if I see 1, 0, have I just seen the entire B, or have I just seen 2/3 of an F? Well, I have no way of knowing, because F is the encoding for B with a little bit extra added on. You could argue that maybe there's a way of figuring it out if you get all the way to the end of the sequence and then try to just sort of jumble everything, like try to fit that into an even number of characters. But in general, we're in trouble in this case. But the actual problem, it turns out, is only caused by this prefix issue. Because this is an applications lecture, this is where I get to breathe a sigh of relief that I don't have to write a proof of this, because I can just say, don't worry, the compression people told us this is how it works. But I hope you can see how the prefix thing is causing a problem. I'm also claiming that it's the only thing causing that problem. So this wouldn't be an issue if the encoding for B were not a prefix of the encoding for certain other things. But the prefix thing is happening in other places as well. So you can see if my sequence starts 1, 0, 0, am I looking at a B followed by the beginning of something else, or am I looking at an E? I have no way of knowing, because the encoding for B is a prefix of the encoding for E. And the slides agree with me, so I've gotten a bit ahead of the slides here. We'll just skip over that. And because in cases like this, there's no way to know, I can't really achieve lossless compression. Even if I could argue that by looking at the entire sequence, I could somehow find a way of breaking it up, that would be very inefficient if it were possible at all. And we'd have to prove it's possible, and we don't want to write proofs today. And I'll just say from on high, it's not possible. This prefix condition is something we need to enforce, that no encoding is a prefix of some other encoding. Okay, so it turns out it's actually possible to find encodings that are prefix-free. So here's an example of a prefix-free encoding. Observe, if I see 2 zeros in a row, the only thing I could be looking at is an A. And so that means I can say there's an A, and we're done with these 2 bits, now move on to the next ones. Because there is no other encoding that begins with 2 zeros. Similarly, if I see 0, 1, that has to be a B. Can't be an A because A is 0, 0. Can't be anything else because everything else starts with a 1. If I see 1, 0, okay, well, there are lots of encodings that begin with 1, but only one encoding that starts with 1, 0. That's the encoding for C. So this is a prefix-free encoding because nothing in the table is a prefix of anything else. Now, if we have an encoding scheme that's prefix-free, quite rationally, we might want to call it a prefix-free code. Unfortunately, so I don't know what to say. I apologize on behalf of the whole compression community for this, but for some reason, some wiseacre 50 years ago or so decided that they actually wanted to call such a thing a prefix code. So this is sort of like flammable and inflammable, which is that they both mean the same thing. A prefix-free code is a prefix code. They actually mean the same thing. So a prefix code or a prefix-free code is some encoding table where nothing in the table is a prefix of anything else. I'm so very sorry. I know that's ridiculous. We can all do better as a community. But it's too late now. The slides are written. The definition exists. A prefix code is a prefix-free code. So what I'm saying is that if I choose to decode my sequence by reading from left to right, then all I have to do is walk through the bits until I find anything that matches an entry of the table. So I read 0, just as the bit 0 by itself, and I'm like, okay, there is no thing in the table that's just a single 0. Okay, so get another bit. Let's try 0, 1. I look at 0, 1. In the table, that means B. So I just have a B, and we're good. That's the end of that. There's no way it could be anything else. Okay, so I look at the next two bits, and it's 0, 1. That's letter B, and I'm done. Now I look at 1, 0. Okay, well, there are lots of encodings beginning with 1. Once I pull in the 0, it's clear that I have a C. Because it's prefix-free, nothing else can begin with 1, 0, so I must have a C, and then I just cross this off. Okay, now I have 1, 1. So I just read the two bits 1, 1, but nothing in my table matches 1, 1. So I bring in a third bit, and I have 1, 1, 0. And I say, well, that matches up with G. So I have a G. And we're done. And you can see that by doing it this way, decoding is relatively painless. I just walk through from left to right. Once I find a character, it's locked in, and I'm never going to have to look at those bits again. The slides agree with this. I'll just skip past this slide. And so notice that this encoding actually compresses my data very nicely. So previously, the last time I was working with a valid encoding, so one that could be decoded, was when I was encoding every character into 3 bits. And that was giving me an 18-byte sequence when I'm done. This new encoding, this prefix-free code, gets me down to 14 bytes. So it's pretty clear it can give me compression advantages, even though there are some characters that encode into as many as 5 bits. But the issue is, I'd much rather encode each A with 2 bits than encode an F with only 3. Because back in our 3-bit encoding, every character was encoded in 3 bits. So I saved a couple of bits on the F, but I spent an extra bit on my A. And given that there are tons and tons of A's, so I think from our original ordering, I think there were 13 A's, that means that by saving 1 bit per A, I'm saving 13 bits. And if I have to spend 3 extra bits or 2 extra bits per F, then I'm spending 2 extra bits, because there's only 1 F in my sequence. So hopefully you can understand the idea here, which is that I want to tailor the encoding length of each character to reflect the value of that character, how rare it is. If it's more rare, I'll pay more for it, because I'm not making that purchase very often. If it's more common, I think it should be cheaper. Now, I've already mentioned this, but I'm going to put it right here. It's important to understand that if the compression scheme uses a specialized encoding that depends on the sequence, so in this case, I derived this table in some way. We haven't seen how I did it yet. I derived this table based on the valuation of characters in my input. So if you gave me a different input, I might want to use a different encoding scheme that reflects the value of characters in that. So if there are like 1,000,000 Fs, I probably wouldn't want to use this encoding table. So that means that I must have tailored the encoding to my input. So if you want to decode this data, I have to give you this table. And it's not like you'd have this table in advance, because the table was generated based on the data. What that means is that I actually have to consider that if I want to send you my encoded sequence, my compressed sequence, I have to find some way of sending you the conversion table as well. And there are clever ways of compressing the conversion table, making it take up less space. But remember that when I talk about the compressed size, I have to consider that in the grand scheme of things, there will also be a bit of overhead, a few extra bytes, maybe 100 bytes as far as I know, for a big input. Like if I have an input that's megabytes in size, I might have to spend a kilobyte of data explaining to you how to decode the data. What I'm arguing is, although that's necessary, and yes, it does affect our results, overall, if we're compressing large files, that extra overhead doesn't contribute that much. And so we can still talk about the compression advantage produced by using these encoding tables that are generated for each individual input. Because suppose I have an encoding table that contains every single character representable in 8 bits. The encoding table would have 256 entries. And there's only so big I can make a table of 256 entries where each entry consists of a bit sequence. That's my argument, is that yes, we have to consider this, and that means that the results that I'm showing up until this point in the slides are a little bit too good to be true, but not to a point that makes this analysis unrealistic. So here's a question. Suppose I give you an encoding table. And so it's an encoding table that maps some individual characters or maybe sequences of characters to bit sequences. How can you easily tell if it's prefix-free? Well, okay, one obvious way of doing that would be to go look at it and just do an all versus all comparison. Like you could just look at each pair of bit sequences and verify that no sequence is a prefix of the other. That would work. And if you have a table of n different things, it would take n squared time to do that. You're just comparing different pairs of entries. Sure, okay, so there's a way of doing it, and it's good to have some way that works. But there's actually a more profound observation we can make, which is that it turns out I could convert any sequence that is mapping characters to bit sequences, so any table like this, I could actually convert that to a binary tree. And the observation I want to make is basically that if I look at the bit sequences, each bit in the sequence is either a 0 or a 1. If I go look at a node in my binary tree and I look at its children, there are only 2 of them. And so I could call those, I could say the 2 different paths I can follow, and this is actually sort of harkens back to decision trees. I could label the different paths where to go to the left is to say 0, and to go to the right means 1. If I do that, I could associate every bit sequence with a path through a binary tree, and therefore I could represent my bit sequences with a binary tree. So for example, suppose I define 0 means left, so 0 equals left, and 1 equals right. Let's take a look at the sequence for G. Okay, so G says right, right, left. Okay, so I start at the root and I follow a path beginning at the start of my bit sequence. I go right, right, left. And we'll just say, okay, whatever node I end up at, that's the node corresponding to G. If I want to know the encoding for G, I just walk all the way back up to the root and keep track of which directions I had to turn. From the root going back downwards, I had to go right, right, left, so G is 1, 1, 0. What about the encoding for, okay, we'll erase. What about the encoding for, let's do B. 0, 1, that would be left, right. Okay, so left and then right. And there I am at B. So hopefully you can see how I can translate any binary sequence into a sequence of directions. And I could then design a tree that matches up with every sequence of directions. So the path from the root to any node, for example, the node labeled G, that would be right, right, left. So 1, 1, 0. I just used the different bits to represent the different directions I could travel. And this gives a nice correspondence that I could use to convert between these 2 representations. All right, so let's prove that. Here is an encoding table that we haven't already seen. Actually, we have seen it. Okay, here's an encoding table we haven't already seen the tree for. It turns out this is the invalid encoding from earlier. So I should obviously read the slide before I tell you what the slide says. Construct the binary tree representation of it. The way that I think we should do this is we just take each bit sequence and add whatever nodes to the tree we need to make that happen. So for A, I'm like, okay, A is go right, then go right. So I just need to draw enough nodes to make that possible. So right and then right, and that's A. B is go right and then left, so 1, 0. So I go right, that's already possible. I add a node down here for B. Hopefully you see what I'm doing. I'm just walking through my tree and adding whatever nodes I need to fill out my directions. Okay, C is left, right. So I go left and then I go right, I'll make the node bigger, and I get the C. And then finally D is left, left, right. Okay, so left, left, right. And then that's the D. So we just go through and do that. There's A, there's B, there's C, there's D, there's E, F, and G. Okay, so I've now generated the binary tree corresponding to my encoding table. Remember that I said this was the encoding from earlier that has a problem. The problem was that those prefixes existed. So the encoding for B is a prefix for the encodings for E and F. My question is, even before the slides get involved, because they're always poking their nose into everything, even before we let the slides weigh in, is it sort of obvious that there's a problem with this tree? Is there a way I could translate the fact that there's a prefix in the table into some observation about the way the tree looks? Another hint would be, so B is the subject of a prefix issue because it's a prefix of E and F, but so is G because G is a prefix of D. Now glance over that tree and tell me if you can't just see some sort of pattern there. So we know this is not prefix-free. We know that E is a prefix, B is a prefix-free, and F. Okay, slides, we're way ahead of this. It actually turns out that we can sort of observe the pattern there, which was, in this case, the encodings that were problematic, B and G, are internal nodes of my tree. And that makes some intuitive sense, because what that's telling me is if I want to get all the way to F, I have to walk through B, because I hit the encoding for B part way along to the encoding for F. Same thing with G and D. I actually end up sitting on the encoding for G before I've actually reached D. So the encoding for G must be a prefix of the encoding for D. And a fact we can now state, something we don't have to bother proving, although I think it's intuitive enough that we might actually have the skills to write a proof of it right here and now, but I won't, is that an encoding is prefix-free if and only if no node of my binary tree representation, no internal node contains a label, basically. In other words, that every single character in my table is in a leaf of the tree. So as I said, there's a few ways of stating that. What I want is for all the internal nodes to be blank. I don't want there to be any character that falls into an internal node of my tree because that implies that there is a prefix. So to have a prefix-free encoding, I need to ensure that the only nodes in my tree with labels are the leaves. Okay, so now a question is, given some set of symbols, how can I construct a prefix-free encoding? There's one really key thing missing from this prompt, and it'll become clear what that is in a minute. So let's just try and interpret this literally. I have a set of symbols. I want to find a prefix-free encoding of those into binary, just any prefix-free encoding. Well, I know that in a prefix-free encoding, the symbols themselves have to be attached to leaves of my tree. So I suppose all I need to do is, so here's an example of a symbol table. Notice how I've chosen here to show off that I am allowed to make individual symbols, individual things that I'm encoding, more than one character in length. So I could make AB be the bit sequence 0010. That's completely fine. There's no requirement that the only things I'm encoding are one character long. I could have pairs of characters or entire words if I want to. That's completely fine. I want a prefix-free encoding of this. Okay, so there are 7 things here. So I suppose all I have to do is make a tree with 7 leaves. So there's a tree with 7 leaves. It's not the only one, but there's a tree with 7 leaves. And then just attach one of my different symbols to each of the leaves. So I take AB and I put it, I don't know, over here, whatever. And then once I have the tree already labeled, I just use the tree to generate the bit sequences. So AB would be left, left, left. That's 0, 0, 0. Let's do AE. AE would be left, right, right. Okay, fair enough. So I can generate the tree, label it, and then go backwards from the labelings of the tree to the bit sequences in the table. Great. But notice that one key thing was missing, which was we didn't ever take into account the value of different symbols. So we've noticed here that Z ended up getting a shorter encoding. It's only 2 bits long. Does it deserve it? Does Z actually occur often enough to warrant getting only 2 bits? Well, we never even asked. We never even considered that possibility because all we did was just map every symbol to a leaf of the tree without considering which symbols deserve better encodings. Okay, fair enough. Let's try a different prompt. Given a sequence of input data and a set of symbols, how can we produce some prefix-free encoding that results in good compression? Really what I mean here is that if I look, so you give me some data, and let's say the data only contains the symbols A, B, and C, so only those 3 characters. And I discover that your data contains 5 A's. And let's say it contains 17 B's. And let's say it contains this number of C's. Isn't it sort of clear which of the symbols deserves a shorter encoding? I think it is. I think I want to find some way of using fewer bits for C. With this model, I don't care very much what order the symbols come in. Like it could be 1A, then 1B, then 1C, then 2 more B's, then 5 more C's, whatever. All I care about in terms of valuing each symbol correctly is how many times does each thing appear overall. So suppose I use single characters as my symbols. One way of figuring out how to price each symbol would be to just count how many times each symbol appears. So suppose I know that. Suppose I know how many times each symbol appears, and I want to find some binary encoding that values each symbol correctly. In this case, I hope you'd agree that I don't think it makes much of a difference if A ends up having a long encoding, as long as that means I can give a really short encoding to C. I could give maybe a 2-bit encoding, or maybe if I'm really lucky, I could encode each C with only 1 bit. Because of course, if I'm saving 1 bit for every time I see the letter C, then I'm going to save a whole ton of bits. If I'm wasting a few bits on A's, who cares? There's not very many A's overall. So I guess what we'll do is consider this problem. I split the text into symbols that are K characters apiece. Let's just do 1 character for the time being. And then I want to find a prefix-free encoding that uses as few bits as possible overall. So not as few bits per individual symbol, but the smallest number of bits if I consider the entire encoded sequence. And so I suppose we want the following properties, which are 2 sides of the same coin. If a symbol appears a lot, I want it to have a short encoding. In other words, I want it to be at a low depth. I want it to be close to the root of the tree. If it doesn't appear very often, I don't mind if it has a longer encoding. I mean, obviously, in a perfect world, every symbol gets encoded into 1 bit, but that ain't happening. So instead, I'm happy to sacrifice some of the symbols that are rare for having to have some long encodings if in exchange I can have short encodings for the more common symbols. So consider this text fragment. Suppose that I choose to use 1 character symbols. So each of the different characters of text is represented by its own bit sequence. What I could do then is just make a table of the frequency of each of my different characters. So for example, A appears twice, R appears 6 times, S appears once. And it's easy to do this. All I do is just walk through my sequence and count how many times each character occurs. And so if I design some prefix-free code that values each character appropriately, I should expect, hopefully, that R, the most common letter, has a short encoding. In exchange, I don't mind if U has a long encoding, because U only occurs once, so if I lose a bit or two on the U's, but I save a couple of bits per R, I'm going to make a profit overall. And the algorithm, which is the point of this lecture that we want to talk about, is called Huffman Coding. And the tree it produces is called a Huffman tree. And I'll talk about why we want to use Huffman coding in a few minutes. First, I'm going to introduce how Huffman coding works. So, the algorithm builds one tree by starting with a large number of small trees and merging them together over time. So what I do is, one tree for each, this is a fill-in-the-blank slide. The algorithm begins by having a single tree consisting of one node corresponding to each symbol. And so here I have a collection of, 11 trees or 10 trees, and I've labeled each tree with its total frequency. So what this is saying is the space character occurs twice, and the character R occurs 6 times. And the goal of the Huffman coding algorithm is to, over time, merge these trees together over and over again until there's only one tree left, and that will be our final encoding tree, our Huffman tree. So we're going to have one tree per symbol. I think I've gotten a correct mark for my fill-in-the-blank. So throughout the algorithm, I'm going to track the total frequency of each subtree. I shouldn't say subtree. The total frequency of each smaller tree. The way I'm going to use this, I'm going to use a count as my frequency. You could also use a probability value. Everything would be exactly the same. You'd still add them together, as we'll see in a minute. So I'm just going to use frequencies because it's nice to work with integer values, and because if you give me a sequence of text, it's pretty easy to compute the frequency of each symbol that appears in the text. All right, so each step of the algorithm does this. It walks through my set of trees, and it goes and picks up 2 trees with the minimum frequency, the lowest frequency. Now, there could be ties, so you can see the lowest frequency among the different trees here is 1. So we just pick 2 of those. We choose the 2 trees that would show up the first 2 elements of the sorted ordering of trees if we sort by frequency. So let's say that's the L and the S. And then, so we choose the 2 with the lowest frequency, and we merge them together. And the way we merge them is we add a new root and then attach it to each of the 2 trees. And notice how we started with 2 trees with frequency 1, and now we have 1 tree with total frequency 2. So the total frequency of each tree is being tracked at each step. And we just repeat that merge step over and over. So at each step we choose 2 trees that have the lowest total frequency among all trees, and then just merge them together. And we always do the merge the same way. We make a new root and then merge it by joining the roots of each of the 2 trees to my new root node. Okay, so the next step, I choose 2 trees with minimum frequency. Now, of course, there's only one tree that has frequency 1. There's a whole bunch of trees with frequency 2. And so for our purposes, the choice of which one to use are sort of arbitrary. And it turns out the algorithm doesn't care that much. But suppose that I choose the space and the U. I have to choose the U, and the other one I choose happens to be the space. So I merge them together. Now I have a tree with total frequency 3. Maybe it's already clear, I guess intuitively, that as I do these merges, the frequency of what I create tends to be a bit higher. And therefore, although I will eventually merge this tree again, by performing this merge, I probably won't merge the U again for a couple more steps, because I probably still have lower frequency trees to work with. Okay, at the next step, I happen to choose the A, which has frequency 2, with this one, which also has frequency 2. You might be inclined to think, why not choose one of the other small trees? And it turns out it actually makes no difference in the end. So although it's weird to start by picking up this bigger tree, it's fine. The total frequency is 2, so it is a candidate to merge, because the minimum frequency available is 2. So any 2 trees with frequency 2 are good candidates for a merge. So I merge the A with the tree involving L and S. And we get this. So notice the merge is the same. I make a new root and join it to the roots of the 2 subtrees I had before. Now I have a tree with frequency 4. Okay, the next step, I choose the P and the Y. I merge them. I have another tree of frequency 4. Then I choose the B and this other tree over here with the space and the U. Merge them. Now it has frequency 6. At this step, I will observe, notice how the 2 symbols that had the highest frequencies are still sitting there and waiting. They have not been subject to any merges at all. On the other hand, the symbols that appeared less frequently have in some cases been merged more than once. So the L and the S both had frequency 1, and they've now been the subject of more than one merge. I've actually merged them once to merge them together, and then a second time to merge them in with the A. Okay, the next 2, I choose the E and the tree involving A, L, and S. I merge them. Now I have a tree with frequency 8. I choose these 2. Finally, the R gets merged. Okay, there it is. And then I choose the 6 and the 8. I merge them. And then finally, I have only 2 trees left, and I merge them as well. You might have a question along the lines of, why do I choose to put this one on the right? It turns out that's also arbitrary. There are, in practice, plenty of reasons why I might want to merge with one tree on the left and one on the right with a certain rule, but in general, the Huffman coding algorithm in general doesn't care about that. All I do is merge them together in some arbitrary order. So I keep merging until only one tree remains. And the tree can have a variety of different structures depending on lots of factors about our input, but eventually, after a certain number of merges, we're only going to have one tree left. Now, notice, as I pointed out about halfway through, that symbols which started with a low frequency, like L and S, were merged earlier and more often. So S and L got merged several times. And we can actually see each merge that involved S and L was one of these empty internal nodes above it. So S and L were involved in what? 1, 2, 3, 4, 5 merges. Whereas R, the most frequently occurring symbol, only was subject to 2 merge operations. As a result, R appears higher up in the tree, or at a lower depth in the tree. It's closer to the root. And therefore, R is going to have a smaller length for its encoding. The encoding for R, I guess, is going to be 1, 1. Versus the encoding for S, which will be 0, 0, 0, 1, 1, so of length 5. So that's a significant difference. The depth of the node, as I observed a minute ago, the total depth of a node is just equal to the number of merges you performed involving that node. So the S was subject to 1, 2, 3, 4, 5 merges, and that's its depth. One other question we might have, and evidence of why it is that we have to put this lecture right after the heap lecture and not before, is if we think about what I did each step of the merging. So I had to go pick out the 2 trees that had the lowest frequency. So how do I do that efficiently? Because I could have tons and tons of trees. Well, one thing I could do is I could just put each tree into a priority queue using the frequency as the key. And then, as I go through the algorithm, at each step, I just call remove min twice to grab the 2 trees with lowest frequency, merge them together, insert the result back into the priority queue. And there's a style problem here. The operation I should be using is insert. So that's a copy editing failure. Add is also a valid name for the operation, but at some point while drafting slides, I chose to call it insert. So at each step, I perform 2 remove min operations to grab the 2 trees with lowest frequency. I merge them, and I insert the result back into the priority queue with the updated frequency. Now, assuming that I was, let's say, to use a heap, which I mean, for priority queues, why not? The merge itself is actually constant. Taking 2 trees and tying them together is pretty straightforward. I just make a node and then set its child pointers, which means what I can do is I can perform, at each step, I'm performing 3 priority queue operations. So assuming I'm using a heap, that means that the 2 remove min operations take, there's 2 of them, and they each take log base 2 of n time. One add operation takes log base 2 of n time, where n is the number of symbols I started with. And that means that overall, if I want to do, because I have to perform n merges over time, I'm going to end up doing n log n operations. So Huffman coding is an n log n algorithm, and it does this by performing 3 log n priority queue operations n times, so n log n. Okay, so that means Huffman coding is pretty efficient. And then once the tree is constructed, all I have to do is traverse the tree to figure out the encoding for each symbol. I already demonstrated that a bit. I just say, okay, what's the encoding for A? Well, so left, 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 0, 0, 0, 0. I can actually do this with a single traversal, probably in order, maybe pre-order traversal. I guess I would want, probably pre-order or in order. And then as I get to each leaf, I just output the sequence of directions I've seen so far. Like I might maintain the current encoding as like a stack or something. So when I go left, I push 0 on the stack, then I push 0, then I push 0, then I push 0. And if I hit a leaf, I'm like, take that encoding, and then in reverse order, that's going to be the encoding of this symbol. So there is a way of doing it with one traversal of the tree to go and produce the encoding table. Once I have a symbol table, so for a lot of reasons, it's quite convenient to be able to say, okay, A goes to 0, 0, 0, 0. L goes to 0, 0, 0, 1, 0. S goes to 0, 0, 0, 1, 1. A table like this is nice because then as I want to actually encode my input, so once I've made the tree, the next thing I want to do is convert my input characters, my actual input data, into this representation. Having a table is great for that because I can just look up each thing in the table and just output the corresponding bits. So I'd end up with a table like this. And hopefully it's clear that this table is quite helpful for if I actually perform the encoding itself. And it turns out that the encoding produced by the Huffman coding algorithm is known to be optimal. So once you've chosen your symbols, so once you've decided that there's going to be one symbol for a space, a symbol for the letter A, and so no two character symbols or whatever, once you've chosen what the symbols in your table are going to be, if you then compute the frequency of each symbol and perform Huffman coding, the resulting encoding, if you then translate it into the binary compressed sequence, will be as small as possible given what you started with. So the choice of symbols is a different deal. So how you choose which things to use as symbols and the choice, for example, to encode each character separately, that's something different. Once you've made that decision, if you use Huffman coding to generate the encoding table, you are guaranteed that the total number of compressed bits in the sequence will be as small as it possibly can be, the shortest possible set of bits. Now, you notice I put a bunch of qualifiers in that sentence. Remember that there are other factors that are involved in determining the compressed size. So for example, I have to, if I encode this sequence with this table and send you the bit sequence is guaranteed to be as short as possible if I use Huffman coding, but I do still have to provide you with this table somehow. And that takes a few extra bits to send over, and that could affect the compressed size. And if I'm not careful, that could mean that somebody else's encoding scheme that doesn't use Huffman coding might actually produce a smaller sequence, as long as if the amount of bits I need to encode this table is unreasonably large. And so I also observed that Huffman coding is what I apply after I've chosen my symbols. So, of course, the choice of symbols is a bit more complicated than the Huffman coding process, I guess. So I could choose to encode each character separately, in which case each symbol is just one character. I then compute the frequency of that, and I go run Huffman coding. Once I've made this decision, Huffman coding gives me the best possible encoding for my choice of symbols. However, there are lots of ways I could choose symbols. So I could observe things like RR, the two-character sequence RR appears over and over again. So maybe it's useful to have a symbol table that involves each symbol is two characters, a pair of characters. Huffman coding doesn't comment on that because Huffman coding is applied after I make my table of symbols. And it's true that depending on how I choose symbols, I might end up getting better or worse compression. It's completely valid for me to choose symbols that overlap even. So I could have one symbol for a Y by itself and one symbol for a Y followed by a space. That's completely valid because if I make a separate encoding for each of these options, I can still decode it uniquely. So I'm trying to put this in the right context. Huffman coding is an optimal algorithm once you have chosen your symbols. But as far as how to choose symbols, you're sort of on your own there. There could be lots of different options, and it may be very difficult to figure out the best one. However, for our purposes, it's good to think about this as being applied, let's say, to single characters. Although there are examples where if you can find a way of figuring out the best combinations using mixed groups, like using R as its own symbol, but the word berry as its own separate symbol, could result in better compression. But that requires inspecting the input data for patterns, something that could be a very difficult problem. And actual compression schemes, including schemes like deflate, do that to some extent. They for example, a scheme like deflate would notice that the word berry appears over and over again in this, and that one way of achieving good compression would be to just make up a special bit sequence just for the word berry. So every time you see 101, you print out those 5 characters. That would be a big savings. But finding that pattern is something that we don't really want to talk about today. But one question we haven't yet answered is, what about the other direction? So it's pretty clear I can do the decoding, but is there a fast way to do it? And what I mean by that is, obviously, if I give you this bit sequence and I give you this table, and we know already that if it's a prefix-free code, which Huffman coding is guaranteed to create, then there is a way of decoding it. And you could do it, I don't know, by brute force, by saying, okay, there's 1, 1, okay, go find it in the table and look it up. But that could be time consuming because I may have to do a linear search of my table to find each bit sequence. I could sort the table somehow and then use binary search, but there is actually a faster way, and it again involves recourse to trees. So the question is, given a symbol table, so I hand you a table and I give you a sequence of bits, is there some efficient way to decompress the data? And the answer turns out to be yes, although in practice, it turns out the way that people tend to use is not this way because this involves a tree traversal, which although it's fast asymptotically, does have a lot of overhead in practice. So of course I could just use some sort of dictionary mapping. Wait a minute, what's a dictionary? Okay, we'll sort that out later, but you're probably familiar with the general idea of dictionaries and associative mappings. So if you use Python, you know what a dictionary is. I could use some sort of dictionary mappings to map encodings to symbols, but that would still be sort of annoying because suppose I want to decode this sequence here. So I pull out a 1 bit and I'm like, okay, what does this decode to? So I go look up 1 in my table. Well, 1 is not in my table as its own encoding, so I try again. I look up 1, 1. Okay, I find an R. Great, so I got an R. So I can cross these off. Now I try 0, 0. No, that's not in the table, so I try looking up 0, 0, 0. And you can see I have to keep retrying if the length of my sequence is wrong. So a straightforward mapping where I just look things up in the table could be a bit tedious and maybe inefficient. Another option, though, would be to create the tree. If I create the tree, I know that each of my bits represents one step in my tree. And so I could just use essentially a sort of ongoing tree traversal as a way of decompressing my data. So I get the symbol table. I then build the binary tree that corresponds to the table. And as usual, I'm using the understanding here that we probably have a small symbol table compared to the size of our data. Usually our compressed data is bigger than this. If my compressed data is 400 megabytes in size, and I have a symbol table that's 256 elements, it's worth the extra cost processing in bits, compressed bits, to build the tree and then use the tree, because I build the tree once and I can keep using it. So I turn my symbol table into a tree, and then I could just walk through my compressed data from left to right and just keep traversing the tree until I see something interesting. So I'll show what I mean by that. The first bit is a 1. So I'll start at the root of my tree, and when I see that 1, I'll go to the right. All right, then I see another 1. So I go to the right again, and I hit the leaf for R. And I observe what that's telling me is the traversal I just did brought me to the leaf R, which means because this is now a leaf, there's nothing below it, that I must have seen the character R. So I output the character R. And then I say, well, because I've now output a character, I'm done with one character, I'm ready to start the next one. So I just go back up to the root and start over again. There I am. And then I see a bunch of zeros. So I go left, 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 left. That must be the letter A, because I'm now at a leaf. So I output an A, and I just return back to the root and keep moving. Okay, so now I see, let's see, left, 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 right, right. Okay, there's the letter S. And see how it's pretty obvious when I need to output a character. It's when I hit a leaf, I just output the character stored in that leaf. Also notice that the total number of steps I'm taking is just equal to the number of bits. That's it. I do one step per bit. So if I have n bits of compressed data, this takes big theta of n time. That's pretty good. Here is some basic pseudocode for that. Now, it's high-level pseudocode because there's some aspects we can't really account for. So, for example, I don't know where you're getting your compressed bits from. Is it some sort of array of bits? Is it something else? I don't know. We'll just call it a data source. And we'll assume, because exactly how I get each bit is independent of the matter of traversing the tree, that's a detail we can fill in on a per-application basis. So I start at the root of my tree, and as long as there are bits left, I just go grab the next bit. If it's a 1, I go left. If it's a 0, I go left. If it's a 1, I go right. If I'm now sitting at a leaf, I output the symbol stored in the node I'm looking at, and I go back to the root and I keep going. And the formal running time of this, if we think about it, so I already said that the process of walking through the tree is big theta of n if n is the number of total bits, because I take one step per bit. But there is one other thing that's sort of hiding in the details, which is number 11, which is that I guess I do need to spend some time outputting each character, because it might be that the symbols themselves, or I shouldn't say character, I should say symbol, I might need time to output each symbol, because the symbols themselves might take some time to output, because it could be multiple characters in length. So I should include the total number of decompressed symbols to try and account for how long it takes me to output them. Although if if each symbol is just one character, then presumably the time it takes me to output a symbol is just 1, it's just constant, and therefore the plus m sort of vanishes, and I end up with just big theta of n. And now a question, I guess, is what is the complexity? If you give me the table, how quickly can I build that tree from the table? And the answer there is we can build the tree by simply taking each encoding in the table and walking through the tree and then adding nodes as we go. And that means that the total running time of the operation of building the tree would just be, well, okay, I do one step per bit in each of the different encodings in the table. So it would be the total number of bits across all encodings of the table, which would be 36 in this example, if it makes much of a difference. And I mean, as a more loose bound, just to avoid having to count a particular table and talk about it in terms of all tables generally, it would be if I have S symbols and each symbol has an encoding which is at most k bits, I could generate the tree from the table in big O of S times k time. All right, so there's our little taste of data compression. And what I was able to show is that there is this really interesting tree-based algorithm, the Huffman Coding scheme, that allows us, once we've chosen a way of breaking up our input into pieces, for example, single character symbols, it allows us to generate an encoding of those symbols into bit strings that accurately reflects the value of the symbol. So symbols that are common are given a cheap value, they're given a small number of bits, whereas symbols that are rare they cost more, they have a larger number of bits. But the Huffman coding, as it turns out, guarantees that when you encode the complete sequence into your compressed sequence, it will be as small as possible for that particular choice of symbols. And that's a pretty big deal. That actually gets us on the road to designing our own compression scheme. Now, of course, real compression schemes often use Huffman coding. So for example, the deflate scheme and bzip and the internals of the JPEG algorithm, all of them use Huffman coding as one of the steps. But there are a bunch of other steps. So for deflate and bzip, there are also pattern recognition steps and certain transformations that are applied to try and improve the efficiency of other parts of the pipeline. For an algorithm like JPEG, or a lossy compression scheme, so JPEG or MPEG-4 video or HVC video, or like audio compression like AAC or MP3, there's also that step that involves attenuating the quality of the data. So removing parts of the data that we think nobody will notice or we think nobody will mind missing. And then lossy compression schemes also employ things like Huffman coding. So the images that you're looking at right now and the audio you're listening to right now very likely have had Huffman coding applied to them. A Huffman tree has been generated by the compressor, and that has been used to both encode and decode the data. So compression, as I said at the beginning, is one of those things that's pretty easy to justify to people is a useful application. And we've seen today lots of ways in which it ties into things that we've already learned in this course. Now, speaking of learning things in this course, I guess we're ready. We've had our breather again, so it's time now to dive in, starting in the next lecture, to binary search trees, which we are going to find we spend a pretty decent amount of time on.